In this video, I want to build up on the concept of the velocity as a vector quantity to transfer this concept onto the acceleration in order to see how we can solve certain problems that involve the velocity with the help of the acceleration. And for this we need to see how we can, in which way the vector properties of the acceleration can help there, and where exactly the connection is between the velocity and the acceleration. So we start with a little repetition. So v is delta s by delta t, and this is a rate of change. So the velocity is the rate of change of the distance in the time, or as of here, in respect of the time here. And we already know that this can be seen as a vector quantity. So now we look at the acceleration, and this is the change of velocity in a certain time. Now we know that the velocity has vector properties, and that means that the acceleration must also be a vector quantity. Now, this is not a very surprising, because we know that acceleration, we can accelerate a body with a low acceleration or a high acceleration, and that means it gains velocity faster or not as fast. But also the acceleration acts in a certain direction. Now this, I write that here in the corner. We already know that F is equal to n times a, and since the force has a certain direction, it comes from the acceleration. So depending on the direction of the acceleration, that is the same direction as the force that acts on an object. So we have been looking at movements before, and we know how to draw them in a diagram. So we start again with a simple example in a TS diagram. And when we see a straight line, we know that this movement has a constant velocity, because we can see in certain time intervals, delta t, we have always the same distance that we travel. This is because the slope or the gradient of a straight line is always the same, and the formula for the gradient is exactly the ratio of delta s and delta t. Now this is already S4, I think. So we move on to a motion that is accelerated. For example, this one here. Now, how can we see that this is an accelerated motion? We see that the slope or the gradient of this graph is changing, and that means that the velocity must change, and the change of velocity is called acceleration. So here we can see that the gradient is getting higher. So the acceleration is greater than 0 or has a positive sign. We also speak about accelerated motion when the velocity is decreasing. In this case, however, we have a negative sign, meaning that the acceleration is below 0. And we see that because the slope is decreasing. Now we start with a little example. Let's consider a car and it is accelerating with, let's say, 5 meters per square second. Now this is a strange unit. Square meters is quite easy to explain and to understand, but a square second, meaning we have 2 dimensions, seconds times seconds, so there can't be an area. So we want to ask the question where this square second comes from. And for that we look at the formula here again. The unit is derived by the formula, and the unit for v is meters per second and t is second again. Now we know when we divide by a fraction, it is meter per second times 1/second, and this makes it a square second. Now it has no practical meaning or interpretation. It comes from basically here it's meters per second, and we want to look at the situation with a car. Let's just put that into a table of values with the time and the velocity as a function of time. So we can consider that at the starting point we have a velocity of 0. Now we have an acceleration of 5 meters per square second. That means after 1 second we already have 5 meters per second. And after 2 seconds we have 10 meters per second. Okay, so this is proportional. We see that because when we double this value, we need to double this value. And so now we could also say that after 1.5 seconds we have 7.5 meters per second. Okay. Now this, if we draw a TV diagram of that situation, it will be a straight line. So after 5, you have, no, after 1 second, we have a velocity of 5, and after 2 seconds, we have the velocity of 10. And here we can see already a lot of similarities between the velocity and the acceleration. You remember before I've deleted that, but I can draw it again. So in an ST diagram, a straight line means that v is constant, and in a TV diagram, a straight line means that a is a constant, because the gradient is constant here and a is per definition the rate of change of velocity. Now we can derive a formula that describes this graph, and this also has a connection to that formula here. So if we multiply by 10, we see that v is equal to a times t. Now you might ask where the t is. This formula applies only to motion where a is constant but not 0. So only if we have this proportional connection between v and t, we see that a is I don't know, the proportional factor, don't know what it's called in English. Okay, so now we want to recall the general equation of movement, which is, I can use a different color here, S is equal to a half a t squared plus an initial speed times t plus an initial distance. Now when we look at this formula in a bit closer, we see that the distance is a vector quantity because it has the length and the direction. Here we have v as a vector quantity, and in the first summand it's a. So altogether we have this. And if we want to extend that a little bit, we see that s is a function of t, because t is the variable here in this equation. We can also already see that this looks a bit like a quadratic function, like this one here is ax squared plus bx plus c. So we see the factor a in this case is half a, by coincidence the same letter but different meaning. The b is the v and c is the s0. And we just replace the x by t. And in the next step we look at the units. So the unit, just to check if the formula is consistent. So we have the unit of acceleration as meters per second squared, and here we have t squared. This is also. So this is the unit is meters. Here we have meters per second times second. So again, that's meters, and here we have meters. Okay, that is meters. So meters is meters plus meters plus meters. That makes sense. So let's look at an example where we have an initial speed of 10 meters per second and an acceleration of -2 meters per second squared. Now we can put these values into our general equation. So we have 2 times t squared plus ten times t. Now you see that I don't write the units into the equation. This is well, in Germany I always expected to have the units everywhere, but since in the bug you have a lot of text and formulas to write and you're short of time, so in the beginning you have the units, then you can leave them out, and the result must always be with the units. So this is t squared plus 10t, and yeah, again, not a big surprise. We see that this must be a parabola, and this is a special one, but we see that later. And we want to do first to see the connection between the v and the a. So we have a speed, and this is a vector, and now we have an acceleration, but it's pointing in the opposite direction. So that means we can't add the two vectors here because we have different units. So we can't say a plus v. That doesn't work. At least not in mathematics. Well, not really in physics, but we did have this formula here. V is equal to a times t. And by multiplying the a with t, we solve the problem with the units, and we create another table of values. And we see that when we put in the time at the time 0, we know that velocity was 10, and we can hang on. Yes. And so after 1 second we have lost a velocity of 2 meters per second, so we are down to 8, 6, 4, 2, and after 5 seconds we have a velocity of 0. Now what about the, oh, I forgot something here. Maybe you've noticed before, there was a -2. So we see here the minus. So here must be a minus. And now we want to reconstruct the graph of this, and in order to do that we find out the zeros before. So when is the distance 0? So that's when we need to solve a quadratic equation. So S is equal to 0, is minus t squared plus 10t. That can be done without the calculator, because this is a special type of equation. Might be easier to write it this way, and then we can 10 minus t times t. And here we can see that this leads to t1 is 0 and t2 is 10. So we know that the distance of the object is 0 at 2 different points, which is, we had the velocity, the initial velocity, and the acceleration given, but we still don't know what kind of movement we are talking about here. So when we draw the graph, we know that it has 2 zeros, and the parabola is it is upside down. So if we draw a diagram with S and T, we've got 1 0 here and 1 here. So in the middle is 5, and there we must have this. Okay. So the highest point is at 5. And now this is a bit strange, but it is not the trajectory of an object, but it's an TS diagram, and there is a big difference. We remember that we have a movement here is only one-dimensional. Okay, so maybe we have a situation where you are running and there is a string, rubber string, or that fixed to your body, or the wind is blowing and you reduce your speed with a constant acceleration. Or we have a ball that is thrown with a certain velocity, but at the same time a force is acting downwards and pulling it, or is decreasing its speed. And we can see that here, that we have the gradient here is the greatest in the diagram, So the speed, the gradient here is 10, and the speed is the highest. Where here we've got something like a turning point. Here the change of velocity, or the change of distance, is 0, so it remains at the same point. The gradient is 0, so here v is 10, here v is 0, and since the parabola is symmetric, we can conclude that v is equal to minus 10 here when it, I don't know, hits the ground or comes back or something. So yeah, that's about all that I wanted to demonstrate here in this video.